Welcome to the second part of our discussion on the 2022 physics practical. If you haven't watched the first part, I highly recommend you do so right away. In the first part, we talked about the experimental setup, we analyzed the nature of the graph, and we also talked about the theory behind this experiment. So I highly recommend you watch that video before you watch this video. In this video, we are going to simulate the electricity experiment of the 2022 Neco Physics Practical. And we're going to use a virtual laboratory known as the Mavinhub Physics Lab, which allows us to perform physics experiments virtually without actually stepping foot into a physical lab. Although your experiment will be a physical one, you'll be expected to do that in a physical lab. But the Mavinhub Physics Lab allows you to explore various settings of the experiment without having to buy any equipment. And just with your device, you can perform several experiments at the comfort of your home. So in this experiment, for those of you that have this application or that intend to download this application, we are going to be simulating experiment 9. Experiment 9 under electricity is what is related to what you are going to see on the exam day. And if you haven't downloaded it yet, check the description for the link to know how to get the application downloaded on your device so that you'll be able to follow along and also demonstrate this experiment and gain mastery by yourself. So the objective of the experiment is to determine the unknown resistance of the standard resistor using meter bridge. So here you have the experimental diagram, and here is the way you should connect it. Although it may not be exactly like this, but you should have your standard resistor here. You should have another standard resistor here. Then your resistance box should be here. Then you have your key, your battery, and here you have the potentiometer and the likes. The apparatus should be given as follows. Then here you have the procedure of this experiment. The procedure is quite straightforward. You change the reading on the resistance box. Once you change that reading, you adjust the jockey on this potentiometer wire. You adjust it until the reading on the galvanometer is 0. Once you get the reading of 0 on the galvanometer, you measure the value of X and also the value of Y. You record all of that. You record X, you record Y, then you record the value of R. Then you change the value of R and repeat the entire process again. So that's basically what the experimental procedure is all about. Then once you are done, you take the reciprocal of R, you take the reciprocal of Y, then you plot the reciprocal of Y against the reciprocal of R against the reciprocal of Y, and that makes up your graph. So we're going to go through all of this using this experiment. So the first thing I want to show you is the setting. You can change the setting and see how the results will change. But for this particular demonstration, I'm going to vary R from 1 to 21 using a step of 4. In other words, R will be 1, 5, 9, and so on. Then the value of R1 is 1 ohm. The value of R0, which is the concealed resistance, is 2 ohms. Then the EMF that we are going to have in this experiment is 2 volts. So let's get started. So here is the laboratory environment, the virtual laboratory environment. On the right, we have our resistance box. And to change the value on the resistance box, you'll find a slider on the left. If you take this up, you increase the resistance on the resistance box. Then if you want to move the galvanometer, the jockey, you switch to X here. Then you move the slider. Once you move the slider, then the jockey moves to whatever point you want it to move. Then you need to, don't forget to insert the key by switching it on or off. If it's off, it means the key is not inserted. If it is on, it means the key is inserted. Okay, so what we want to do now is to follow this reading. The first reading is when R is equal to 1. So when R is equal to 1, what do? We just move this slider to 1 here. So the resistance on the resistance box is 1. So what do you do next? What you do is you take the you then let's turn on the switch, that is insert the plug. Then we move the jockey along the potentiometer wire until the galvanometer reading is 0. So you move it until you see that the galvanometer is moving towards 0. You can see that the galvanometer is moving towards 0. Then we now have something very close to 0. So let's move this a little bit. So now at 60, the galvanometer reading is 0. Okay, you can even use this magnifier to see clearly whether you've got your pointer at 0, and that seems to be the case here. So now what do? You just take this, you move to the reading section, you type the reading here 60, then the value of y is 100 minus 60, which is 40. Then the reciprocal of y is 0.025, that's 1 divided by 40. Then the reciprocal of r is 1. So for the second reading, the value on the resistance box is 5. So you just go to the lab section, you go to this R, then you move this to 5. Now that you have the value of 5, the next thing you want to do is to switch to the jockey section. That is, you move your jockey until your reading is 0, on the reading on the galvanometer is 0. So what you want to do is to make sure you get something very close to 0. You can even confirm. Here we are almost at 0, not exactly at 0. So what you want to do is to move this until you get something very close to 0, and that is somewhere around. So what you want to do is to adjust, keep adjusting. So let's keep adjusting until we get something very close. So at 41.18, roughly this, we have our pointer at 0. So let's record that. So x is 41.118. Then 100 minus 41.18 we give 58.82. Then the reciprocal of y is equal to 0.017. Then the reciprocal of r is 0.2. For the third reading, the value of r is 9. So what you want to do is to switch back to R, move this until you get 9. So the resistance box here is the reading on the resistance box is 9. Then you want to move your jockey until you get to 0, until the reading on the galvanometer is 0. And in this case, we just keep adjusting until we are confident that it is at 0. And that is somewhere around 38, let's say 30, like around 38. It's almost at 0. So let's probably decrease it a little bit. So let's say 37.9, roughly 37.9. So what we want to do here is to say this is 37.9. Then the value of y is somewhere around, is 100 minus 37.9, and that is 62.1. So the next thing we want to do is to take the reciprocal of y, and that will give you, the reciprocal of y will give 0.016. Then the reciprocal of r will give 0.111. So what next can we do here? The next is to move on to the fourth reading, which is 13. So the value of r is 13. So you move this up until you get 13. Then you go back to X and adjust the jockey until you get the reading on the galvanometer to be 0. And at this point, we are close to 0, almost 0. So you can adjust a little bit to see the direction it goes. So this is the best I could get. That's 36.6. So here we have 36.6. Then the value of y will be 63.4. Then the reciprocal of y is going to be 0.016, 0.016, or to be a little bit more precise, let's say 58. Then we have the reciprocal of r to be 0.077. So the next thing I want to do is to take the fifth reading. The fifth reading is as follows. You take you move this to 17, you add 4 to it. We are moving at a step of 4. Then you switch back to X, and then you take your reading. You switch back to X and you adjust your jockey until you get the reading on the galvanometer to be exactly on 0. So that's at 35.81. So 35.881. But let's adjust a little to see if we can get something better. So the best we can get is this 35.8. So can we get better? No, we can't. So that's 35.8. Then the y is 100 minus 35.8, which will yield 64.2. Then the reciprocal will roughly give us 0.0156, roughly this. Then the reciprocal of r will give 0.059. Then let's take a look at the sixth reading where r is 21. So you switch back to r, then you move this up to 21. Then you switch back to the jockey, then you adjust the jockey until you get to 0. So you gradually move it until you get to 0. Let's check if we've gotten to 0. This is the best we can get. So that's at 35.4. So this is 35.4. Then we do the same. We take the difference, 100 minus 35.4, that's 64.6. Then the reciprocal is somewhere around 0.0155, roughly this. Then the reciprocal of r is 0.0476, or we can just say 7. 0. Let's say 8 if you approximate to 3 decimal places. So this is what we have as our reading. So we are done with the reading section. So the next section is the graph. To plot the graph, what you want to do is, to get a good graph, you want to get the title done. You want to label the x-axis, the y-axis, and every other thing. I won't go too in depth into how to make a good graph here. We've made a video on how to make a good graph. So look out for the video and go and watch that, because we explain in detail. We provided a clear explanation on how to make a good plot. So check that out. Here I'm just going to apply that principle, and so that we can quickly see how the graph looks like. How it looks. So the first thing I want to do is to provide all the titles. So in this case, the title is the we are looking at the inverse resistance, the inverse resistance versus the inverse length, inverse length. You can call it length J, Q, or whatever length we are dealing with. In this case, we are looking at JQ. Then what about the x-axis? For the x-axis, we are talking about the inverse of y, so 1 over y, and the unit is centimeter raised to the power minus 1, basically. Then for the y-axis, we are looking at 1 over r, that's 1 divided by r, and the unit is ohms, the inverse of ohms, right? So we can put it this way, ohms raised to the power of minus 1. So just to indicate what it's going to be. Then the next thing I want to define is the range, the range of on the x-axis and the range on the y-axis. I'm not going to go into details. If you want to know more about how I arrived at it, watch our video on how to make a good graph. So for this particular case, I'm going to use the following range. For the x-axis, I'm going to use a range of 0 points. The minimum will be minus 0.005. The maximum will be 0.03. Then I'm going to use a step of 0.005. Then for the y-axis, I'm going to use minus 2.5. Then for the maximum, I'm going to use 1.5. And for the step, I'm going to use minus 0.5. So this is the nature of the plot. The reason why we are using this kind of range is the graph is going to run through the negative axis. So you have to factor that in. Since it's going to run through the negative axis, you want to make more room for that. So what's the next phase? The next thing is to indicate this point on the axis, on your graph rather. So in other words, you need to identify where where all these points are on the graph. To locate the point on the graph, you click on this pencil, on this graph point pencil. It turns purple and you are free to indicate where each point are. So for the first point, 1 over y is 0.025, which is somewhere here. Then the value of r is 1. So you're going to click this point where you have that's where 1 over y is 0.025 and y is 1. Then the next point is where 1 over y is 0.017. So which happens to be somewhere here. This is 0.17, right? Then on the y-axis, 0.2. 0.2 is somewhere here. So 0.2 is somewhere around here. So you click on this. Then for the rest of the region, I'm going to quickly run through them. Now I'm done with the location of the points on the graph. So the next thing is to draw the line of best fit. To draw a line of best fit, you click on this graph line. It turns purple. Then you can draw your line of best fit. So in this case, I want the line of best fit to go through this point. So I'm going to click the starting point. Then I'm going to allow the line to run through as many points as possible until it touches the y-axis. So now we have our line of best fit touching as many points as possible. So here we have our line of best fit. You can clear it if you feel you didn't do a good job, then you redraw. So in this case, I may want to redraw it to see if it goes through as many points as possible. So now we have our line of best fit. So the next thing you want to do is to determine the slope. To get the slope on any line, using this application, you click on this graph slope, then you pick any point. So I'm going to pick this point, then I'm going to pick this point. Once you've done that, the next thing you want to do is to let me clear it and get it done properly. So I'm going to pick this point and this particular point. So what we want to do is to determine the change in y and the change in x. To get the change in y, you can take this to be your first point and you can take this to be your second point. So if this happens to be the first point, it means the value of y here is 0. The value on the y-axis is 0 and the value on the x-axis is 0.015. If this happens to be your point 2, then the value on the y-axis is 0.5 and the value on the x-axis is 0.02. So this is 0.02. The next thing is to take the difference between y2 and y1, which is 0.5, and the difference between x2 and x1 is 0.05. So now we have the change in y and change in x. So let's divide. Change in y divided by change in x will give us the slope is 100. But please note that I made a mistake earlier. For the change in x. For the change in x, the value is 0.005. In other words, 0.02 minus 0.015 is 0.005. So if you divide 0.5 by 0.005, you are going to get 100. Then we'll move on to the intercept. For the x-intercept, that is the point where the line of best fit touches the x-axis. That point is 0.015. For the y-intercept, the value is minus 0.15. So we are done with the graph part of this experiment. You'll be asked to answer some questions. So these are the likely questions you should be expecting. So from the graph, we are asked to look for the value of L divided by S. Here, L is 100, S is the slope, right? And if you look at this, L is 100 divided by slope. Our slope here is 100. We got 100 as our slope. This means that ratio will be 1 if you divide. So for the second question, we were asked to calculate the unknown standard resistor R naught as follows: minus K divided by 1 plus Ck. So let's take a look at this K. K is what we got earlier. K is what we got here earlier. So if K happens to be 1, what that means is we just say minus 1 divided by 1 plus Ck, where C is the y-intercept. So let's calculate this. This will give us, if you perform this computation, you're going to get 2 as your answer. In other words, if K is substituted as 1, and if you replace C with minus 1 over 5, the minus 1 over 5 is the y-intercept. If you substitute both values, you are going to get 2 as R naught. Then let's look at the third question. The third question is just a question about EMF. So if the EMF of a cell is greater than the terminal potential difference, the question is, as long as the internal resistance of that cell is 0, can we say that statement is true? Can we say the EMF is always greater than the terminal potential difference? Well, in this case, the answer is yes, because EMF is the voltage when the circuit is open. Once you close the circuit, once current begins to flow, whatever you're getting from your battery is now the terminal potential difference. And that terminal potential difference is going to be less than the EMF due to the internal resistance of the cell. The next question, the last question, is all about this. So I'm not going to get this solved. If you want to get the answer to this and get detailed explanation to this question, get the application, download the application and perform this experiment. So I'm going to submit to see my performance. Okay, so here we have the report. This application provides detailed analysis on how you perform on every aspect of the graph. So in this particular case, I performed well on the reading, I performed well on the graph section, but it appears my intercept is a little bit off. Let's take a look at the y-intercept. Okay, we got a very close result. Then the x-intercept, we got a very good result, similar to what we have over there. But anyways, this result is the computer generated result based on the theory behind the experiment. And your answer or your reading should be close to the ideal result. It may not be exact, but it should be close to the ideal result. So this is how you perform this experiment. And if you want to explore further, get the Mavinhub Physics Lab and get detailed analysis on how you perform on different settings of this experiment. All the best in your exam.